As long as I can remember, I wanted to be a scientist. I had an aquarium. I was playing with fish, experimenting with conditions. I'm from Bulgaria, but I've been in America for 20 years. I was always interested in advances in medicine, and I think that I kind of generally had the ambition of actually making a difference. When I finished graduate school, there was really an expansion of this genomics, genetics approaches in biology, and a lot of need for computationally trained scientists to enter. I'm in the immunology group where we study diseases like type 1 diabetes, lupus, atopic dermatitis, asthma. So I work on this new technique which is called single-cell transcriptomics or single-cell analysis. It's a very high-resolution understanding of what cell types participate in the immune response, how the immune response against one's own body is mounted, and how we can bring it back to the healthy state. We actually need to use a lot of computational tools to kind of put the data in the format that is actually possible to ask biological questions from. All the cells in their body have the same DNA, and yet all of these cells look very different. Right? Your skin is very different from your blood, it's very different from your eye. The reason is that each cell uses its DNA differently, the way that you would use a recipe book. So you can think of your DNA as a recipe book and then your cells as the cooks. Single-cell technology is measuring how the cells use the recipe book. Before we could look at single cells, all we could look at was how the tissue behaves. So basically we could look at the blood of the patient and we could distinguish how the blood of the patient is different from the healthy individual. But the blood is a very complex organ, right? It has a lot of different cell types that compose the blood. And so what we can do with single-cell technology is we can look at individual cell types in the blood, what they do, and target them individually. For example, we can make a pathogenic cell type less abundant using certain methods of targeting that we have. So essentially, you can think of your tissue as composed of different cells the way that, let's say, a party is composed of different people in the room. And most of the people in the room are good, and then there are some malicious guests there that really need to be thrown out of the room. And rather than stopping the party altogether, you can actually identify who these guests are and escort them out. So that's kind of what this single-cell approach gives you. I guess the same bad people will appear at different parties. And so first of all, it would give you a connection across diseases. And second, it would allow you to get a handle on the cellular threats to your body. So we use a computational approach, an artificial intelligence approach, to identify the way that the DNA is being used in those cells. So you have 25,000 genes that are measured in 1 million cells. What are you going to do with this information? You cannot even open the Excel file, right? So you have to actually come up with modern ways to understand what are the patterns in the data without ever reading the raw data. AI is only beginning to have impact. We have a notion that it will really transform the way we can predict at the individual patient level the outcome, but also in the way that we understand disease. Artificial intelligence will be one of the key pillars driving medicine forward. We're going to do this again.